We'll now learn about some three-dimensional solids called regular polyhedrons or platonic solids. It's section 4.3 in the text. First of all, we need some vocabulary that I'm sure you have heard before. A polygon is a two-dimensional figure, a plane figure, that has straight line segments for its sides. For example, this would be a polygon, or a rectangle is a polygon. It has four straight sides. A circle is not a polygon because its sides are not only straight line segments. Now, what does it mean for a polygon to be a regular polygon? Well, it means that it is a polygon that has exactly the same length to all its sides, and all the angles are equal measure. Here it says, in Euclidean geometry, a regular polygon is a polygon, in other words, a planar figure with straight line segments for its sides, that is equiangular, all angles are equal, and equilateral, all sides have the same length. So we have many of them. We have an equilateral triangle. Let's see if we can think of how many there might be. Here we have the equilateral triangle, meaning that all the angles are the same, all three angles and all three sides are exactly the same length. Now we know that the sum of the three angle measures is 180 degrees. So each one of these angles then is 60 degrees. And that will be of some importance to us as we move on. A square is the regular polygon that has four sides. And of course we know that the sides of a square are all the same measure. It is equilateral. And we know that all of its angles are right angles, meaning all of its angles are 90 degrees, so it is equiangular. A pentagon is with 5 sides to it, and you can see that drawn here, a 5-sided regular polygon. I would like to show you how we would calculate the angles of the pentagon. If you look at any of these, you can put a dot in the center, and you can think of, in this case, 5 triangles. And the sum of the degrees of any one of the 3 angles in one of those 5 triangles is 180. And of course, the inner angles are all the same. So 360 divided by 5 is 72. So each one of these inner angles here is 72 degrees. And if I take, let me take a different color. If I mark all of these angles here, you can see that they're all exactly the same. All the little yellow dots are an angle of equal measure. So if we take 180 degrees and subtract 72, we get 108 degrees. And so 108 degrees is 2 of the yellow dots. So that means then that our angle here is 108 degrees because it's 2 of the yellow dots also. Now for the hexagon, we need to know the measure of its outer angles too, this angle right here. We'd like to know what that is. And so if you think of the six little triangles you could form here, sorry, each one should look exactly the same. We would have 360 divided by 6 is equal to 60 degrees. So in the inner part here, we have 60 degrees all the way around. So that leaves us with, I'll put these two angles summing up to 180 minus 60, or 120 degrees. So if these two add up to 120, that means that this angle here, which is also two of the purple dots, is 120 degrees. So look at our outer angle as we increase the number of sides. This three-sided or the equilateral triangle had 60 degrees in each of its corners. The square, 90 degrees. The pentagon, 108 degrees. The hexagon, 120 degrees. And you can see that the measure of this angle here gets larger. So instead of calculating it for the seven-sided figure, we'll just note that we know that this angle here is going to be greater than 120 degrees. And it continues. Well, how many regular polygons are there? Even though with a drawing instrument it might get increasingly difficult to draw the polygons, the regular polygons with greater and greater number of sides, how many are there? Well, there would be infinitely many, right? There are infinitely many regular polygons, and they begin to look more and more like circles. But really, mathematically speaking or geometrically speaking, there are infinitely many. They just wouldn't look any different to us. Once we got to 20 sides and you go to 21 sides, it would be almost impossible for us to see the difference between them. They would begin to look like circles. But these first 5 here are going to be, well, actually, the first 4 will be important to the rest of our study in this video. So now we can describe a polyhedron. Notice I'm not saying a regular polyhedron, just a polyhedron. A polyhedron is a three-dimensional solid, 3D solid, that has faces that are all polygons. In other words, it has flat faces that are all polygons. This one, it looks like all of the faces are triangles. And let's define some important. This is just an example of a polyhedron. Let's define these important terms here. A vertex, well, the vertex are the points where the faces come together or where the edges meet. And we can see in this case that we have 1, 2, 3, 4, 5 vertices. The face is a polygon. It has a number of flat faces. In this case, it looks like there are 1, 2, 3, 4, 5, 6 faces. And the edges are the lines or the line segments, the edges where two faces meet. And so if we were to count these, in this one it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So we can usually count the vertices, the faces, and the edges of a polyhedron. Here's one more quick example of a polyhedron. You see that it has vertices. I drew this one so it's not as clear. Vertices. It looks like there are 5 of them. And it has faces that are polygons. It looks like it has 1, 2, 3, 4 faces that are triangular. And it has one face on the top that it looks like it might be a square. And it has edges. And the edges are 1, 2, 3, 4, 5, 6, 7, 8 edges. So here we see 8 edges and 5 vertices. Become comfortable with this vocabulary. It actually helps you to learn the material. And it has polygonal faces, a square, and 4 triangles. So a polyhedron was just a 3D a 3D solid with faces that are polygons. But we want to define a regular polyhedron. That's what this section 4.5 is about. A regular polyhedron, or a platonic solid. A platonic solid is a polyhedron whose faces are identical regular polygons. So that's the first part of the definition. The faces are identical regular polygons. For example, in the cube here, we see that the faces are identical squares, and in this one here, the tetrahedron, we see that the faces are identical equilateral triangles. But there's another part of the definition. The faces are assembled in the same way around each vertex. The faces are assembled the same way. Well, what does that mean? That means, I think this is easier for you to remember. Same number of edges at each vertex. There is the same number of edges, or you could say there is the same number of faces meeting at each vertex. So let's look at our cube. We see that we have identical square faces, the first part of the definition, and the second part, we have 3 edges coming in to each of the 8 vertices of this regular polyhedron. Therefore, it is regular. For the tetrahedron, we see that we have 4 triangular faces. They are all identical equilateral triangles, and at each vertex, you see that there are 3 edges coming into it. So these both are regular polyhedrons. Okay, here we see a picture of 2 polyhedrons. Their faces are made of polygons, 3D objects. The second one I had to draw again. That particular picture didn't appear. So why are each of these polyhedrons not regular? Well, what you see on the soccer ball right away is that some of these faces have 6 sides. They are hexagons. This is a hexagon. This is a hexagon, but this is a pentagon. Only 5. So the faces are not identical polygons. Therefore, it is not regular. Over here, notice that at this vertex, we have 4 edges coming into it, and at this vertex, we only have 3. So 3 edges coming into this vertex, 4 edges coming into this vertex, or 4 faces meeting at that vertex. Therefore, it is not regular. You have 2 parts of the definition of a regular polyhedron. Now, the main purpose of this video is to convince you that there are only 5 regular polyhedrons. And to prove this, you have to keep 2 things in mind. One, that if you build a polyhedron, there are at least 3 faces that have to meet at each vertex. You couldn't build a polyhedron with only 2 faces meeting at a vertex. It wouldn't be, well, I don't know what word to imagine 2 faces here. If you had 2 faces, we could have one face coming like this and maybe another face like that, but you've got to have something fill in here. you'd have to have another face in order to make it the vertex, to make this the vertex of a polyhedron. You have to have at least 3 faces. The total number of degrees at any vertex has to be less than 360. For example, imagine if we took 4 squares and put them together like this. If we took 4 squares and put them together, joining them at that vertex, well, they would lay flat on the table. They wouldn't give us the 3D that we want. So the total number of degrees at any vertex has to be less than 360. This would be 4 times 90, or 360, and you see it doesn't give you a 3D corner. So these 2 things we keep in mind, and we will show that there are only 5 that we could build with those 2 things in mind. There are 3 ways that we could build a regular polyhedron with faces that are equilateral triangles, 3 sides. Okay, so we're going to see that there are 3 that we could build using equilateral triangles. If we join 3 of them, at each vertex, we'll be able to do it. Because each angle is 60 degrees, and the total number of degrees at each corner or each vertex would be 3 times 60, or 180 degrees. The total number of degrees at each vertex, adding up 60, 60, 60, we get 180. The octahedron we also get by using triangles. Here we put 4 faces together at a vertex. 4 faces, 4 edges coming into each vertex. Well, you have 4 equilateral triangles, and each angle here is 60 degrees. So we're going to have a total of 4 times 60 degrees, or 240 degrees. And you can see that this opens up a little bit more than this one at each vertex. We have 240 degrees there. How about 5 of them? Well, if we try to hook 5 together, it does work. It's opening up a lot more. You see it's getting a little flatter here. But here we are joining 5 triangles at each vertex. And so we get 5 times 60, or a total of 300 degrees at each vertex. Now, if I try to use 4, what will happen? Well, let's see. If I tried to use, if I tried to use 6, triangles, well then, I would have 6 times 60 degrees, which would give me 360 degrees at the vertex. And what that would mean was that it would just simply lay flat on the table, and we would not have a 3D corner. So if we're using equilateral triangles as our faces, there's only 3 ways that we could put them together: getting the tetrahedron, the octahedron, and the icosahedron. Now, if we go from the equilateral triangle to the square for faces, then we know we have the cube. We have the cube made with square faces. And notice that there are 3 faces joined at each vertex. And each square here, each square has 90 degrees. So 3 times 90 is a total of 270 degrees at each vertex. If I tried to use 4 squares, if I tried to join 4 squares, well, then they would lay out flat, wouldn't they? We'd get something that just looks like this. Each of these is 90 degrees. 4 times 90 degrees would be 360 degrees, and it would lay flat on the table. We would have no 3D at that corner. So we can't use 4 squares, and of course we can't use 5. That's more than 360 degrees. So we only have one. We can join 3 squares at a vertex, and that is what gives us our regular polyhedron, the cube. Now let's see if we can join pentagons together, regular pentagons. We know that each angle, here's a pentagon right here, each one of those little angles in the pentagon is 108 degrees. And we have to join at least 3 of them together in order to have a polyhedron at all. So let's see, if we put 3 faces together, if we put 3 faces at each vertex, we would have the total degrees being 3 times 108, and that is 324 degrees, and it's less than 360. So it's flattening out up here, but it is not flat. So it's 324 degrees at each one, and we can do it. So if you fit your pentagons together like this, you get what is called the dodecahedron. Now, of course, we cannot put 4 of them together. If we tried, let's write that, we can't join 4 pentagons at a vertex. Why? Well, because 4 times 108 is bigger than 360 degrees. So, of course, we're not getting the 3D effect. We have to have the total number of degrees less than 360. So far we have 5 regular polyhedrons. 3 made with triangles, 1 made with squares, 1 made with pentagons. And now, how about hexagons? Well, notice if we join hexagons, 3 of them, if we join hexagons, we get, well, each of these angles is 120. So we have a total of 360 degrees at each vertex. So we are not getting 3D. In fact, we could tile a floor with hexagons, but we can't join them to make a 3D polyhedron or regular polyhedron. So there are none. And as you go up, heptagons, of course, have angles larger than 120, so we certainly cannot join 3 of them together. So what we've proven here is that there are only 5 regular polyhedrons. And here they are: the tetrahedron, the cube, the octahedron, the dodecahedron made with pentagons, and the icosahedron.